after knowing the definitions of the trigonometric functions, we can actually use them to derive some fundamental identities. So I will give a brief proof of some of those fundamental identities because it will be helpful for you to understand why it is true for any theta, for any angle, right? This identity means it's always true, no matter the angle. Fundamental identities. First, I want you to just focus on the reciprocal identities. Reciprocal identities. And if you recall the definition of sine and cosecant, from definition, we can observe that sine is y over r, cosecant is r over y. So suppose they're both defined, and these two numbers, the sine theta, cosecant theta, will be reciprocal to each other. So it's easy to understand that sine is reciprocal of cosecant, and cosecant is also reciprocal of sine. See, as long as the sine is not zero, right, we can do reciprocal. For the similar reason, that means using definition of cosine and secant. So let's see if cosine is defined as x over r, secant defined as r over x, and these two numbers are reciprocal to each other. So immediately we can conclude that the cosine is reciprocal of secant, and secant is reciprocal of cosine. So that means if you know one, you can find the other. Suppose they're both defined, they're reciprocal to each other. So of course, when you calculate secant theta, for example, using the reciprocal, then that requires cosine theta is not zero. If it's zero, then if cosine is zero, then secant is undefined. So we have to be careful. So suppose none of the denominators is zero, then we can say they're reciprocal, right? We can use one to calculate the other. And another pair of trigonometric functions, tangent, cotangent. So yeah, so we can see that tangent is y over x, cotangent theta is x over y. And these two numbers are reciprocal as long as they are both defined. So immediately we have another reciprocal property, like tangent is reciprocal of cotangent. And on the other hand, cotangent is reciprocal of tangent. Yeah. So that means whenever you know tangent, you can find cotangent, vice versa. So the reciprocal identities are always true for any theta. So this theta, as long as both functions are defined and the reciprocal identity will be true for any theta. So to summarize, we see the reciprocal identities, we have 6 of them. Sine, reciprocal of cosecant. And then cosecant, reciprocal of sine. And so they are reciprocal to each other. Cosine, reciprocal of secant. Secant, reciprocal of cosine. Tangent is the reciprocal of cotangent. Cotangent is the reciprocal of tangent. Okay, so we have 6 identities, and they can serve you whenever, but if you know it, then let's take a look at this problem. So this problem, we are looking for tangent alpha. For this alpha, we know it's cotangent. We know the cotangent alpha is 3/7. And what is tangent? So, and if you remember that a reciprocal identity, so tangent alpha must be reciprocal of cotangent alpha. So if cotangent alpha is 3/7, you see reciprocal of 3/7 will be 7/3. So that is using reciprocal identity. Let's work on the second problem. Secant, we're looking for cosine. So actually we're looking for secant using the cosine value of beta. So again, recall that secant beta is reciprocal of cosine. So if cosine is square root of 3/2, reciprocal of cosine is 2 over square root of 3. And of course, you can rationalize the denominator by multiplying square root of 3 to both numerator and denominator. So the final answer can be written as 2 square root of 3 over 3. So that is the secant beta after we applied reciprocal identity. We can determine the secant. So that is the application of the reciprocal identity. Another group of properties is called quotient identities. So let me write the quotient identity. Quotient identities, if we calculate tangent theta, we can use sine theta over cosine theta to calculate tangent. That's quotient. Quotient of sine and cosine will produce tangent. How do I prove it? So let's give a quick proof, because recall that sine theta is y over r. Cosine theta is x over r. So you see the sine over cosine. Here, x, y are the coordinates of a point on the terminal side of theta. So we know that the meaning in this expression. So xy is simply a point on the terminal side of theta, right? The point has xy coordinates, and r is that quantity. That's the distance from the point to the origin. So r is always positive, y over r divide x over r is same as multiplying r over x. You see, divide a fraction is same as multiplying reciprocal. So then r is always positive. We can cancel this. Then we get y over x, which is tangent. Y over x is tangent theta. So we actually proved by using this quotient, and finally we can obtain the y over x, which is tangent theta. We just proved this identity we call quotient identity. So there's another quotient identity that is a cotangent theta. So let me write it. Cotangent theta is cosine theta over sine theta. So if you divide cosine theta by sine theta, you get cotangent theta. How do you prove it? So we can just use the similar method. So let's go from the more complicated side to the other side, right? Let's just divide cosine theta by sine theta and see if we can eventually get cotangent theta. So right now we don't know yet. We are going to show it. So let's use definition. So cosine theta, so still we're considering using the point on the terminal side of theta. So the cosine is x over r, right? So x over r. Sine is y over r. So this x over r divided by y over r, which is same as multiplying the reciprocal. So when you divide a fraction by another fraction, it's the same as multiplying the reciprocal of the second. So, okay. So now divide y over r is same as multiplying r over y. So now we can continue. Because this r is positive, we cancel, so x over y is left, which is cotangent. So we have proved. So this is a quick proof for this quotient identity. And we have done a quick proof of the other identity. So we have two identities. They are called quotient identities. So this quotient identities, what do you use it for? Suppose I know sine, cosine, that means I can discover tangent theta, cotangent theta. Yeah. So I just simply do a quotient, right? Sine divided by cosine, I get tangent value of theta. And cosine divided by sine, I can get cotangent value for theta. So those are the applications. If you want to use these quotient identities, that means you can find values of other trigonometric functions, like for sine, tangent and cotangent, using sine, cosine. Okay, another group of identities, they are called Pythagorean identity. Why they are called Pythagorean identities? Because r squared is x squared plus y squared. That is for triangle, we use Pythagorean theorem. We have this. And because of this, we can derive some identities for trig functions. So let me show you the three Pythagorean identities first. So yeah, here this is the first Pythagorean identity. Sine square theta plus cosine square theta is 1. For any theta, this is true. So can we give a quick proof to this? Yeah, for this identity, let's try to prove it quickly. Again, for the theta, right? You pick any theta, arbitrary theta, assuming sine, cosine are both defined. And then the sine would be, again, don't forget, we pick a point on the terminal side of theta. The point has xy coordinates, and we can also use xy to calculate r. We know that part very well. And then we can calculate sine. Sine is simply y over r. So y over r. But you see, if r is square root, if you do the square, then you get rid of the square root, right? It's simply r square will be x square plus y square. Yeah. So y over r, if you square it, that is the sine value squared. And cosine theta is x over r. Yeah, this is r with the square root. So x over r, but square of cosine. And you do the sum of the squares. What do we get? Do we get 1? The question is, we're trying to show it is always 1 no matter which theta, as long as sine and cosine are defined. And then you can do the calculation this way, you will get always 1. Let's see if we can reduce this quantity to 1. So if we add them, let's square the first quantity. I get y, the numerator squared, the denominator squared. The second quantity, right? A numerator squared, denominator squared. Oh, I noticed that the two fractions have the same denominator. Then we can simply add numerators while keeping the common denominator, which is this. Add numerators. But look at this numerator. It is the same as denominator, right? Because denominator is x squared plus y squared. The numerator is y squared plus x squared. The same quantity. So that means we get 1. So we just proved. You see, for this first identity, we prove that the left-hand side is equal to the right-hand side, which is 1. So we just started from the left side. We arrived at 1, which is the right-hand side. So the first identity is always true. Now, how do I prove the second identity? Yeah, and why let's understand the first identity is called Pythagorean identity. It is because we use x squared plus y squared is r squared. We can simply apply. You see, this is r squared, right? If we apply Pythagorean theorem, that is simply r squared. This is also r squared. Yeah. So, and you end up with r squared, but the same quantity is 1. So now, so that's the first version of the Pythagorean identity, we have three different identities in this category called Pythagorean identities. So the second one, let's again start from one side. Suppose I'm from the left side. The left side is actually 1 plus, recall that tangent is 1 over x, right? Again, the x, y are the coordinates of the point on the terminal side of theta. So, but if you do square of tangent, that means you will square numerator denominator. So that is square of tangent. So I'm starting from the left side. Now, can I get to the right-hand side? Let's work on this. So this 1, let's rewrite it as this, x squared over x squared. So I can conveniently add the two fractions. Because 1, after I rewrite it as x squared over itself, that is a 1, right? So then I can keep the common denominator, add numerators. Now, do we see that x squared plus y squared, the numerator is simply r squared? So r squared over x squared, did we apply the Pythagorean identity? Yes, we did, because x squared plus y squared is r squared. That's the Pythagorean identity. So that is why, yeah, so we apply Pythagorean theorem then to derive this identity. That's why this is called Pythagorean identity. Yeah, so then now in the derivation, simply you see r over x is what? R over x is the secant function. So this is the secant function squared. We arrived secant theta square. So where do I put square? You can put parentheses squared. Usually we can put on top of the function name. Yeah. So what we did is to go from the left side, and we started to work on it using definition, and then step by step we try to rewrite it. And then finally we arrived at the right-hand side. So we proved, again, we proved another identity by using the Pythagorean theorem. So this is another identity, also Pythagorean identity. So, and one more, so you can try to do it yourself. So I just want to show you the 3 Pythagorean identities, and you might want to ask what is the use and try to see the relation. That means for any theta, if the 3 identities are true, then you will be happy, like you can find sine if cosine is given, right? You can try to determine the cosine if the sine is given. So like these two are related because of this equation. So knowing one will help you know the other function value of theta. And because of the second identity, tangent and secant function values are related. So if you know tangent theta, you can use this identity to determine the secant theta. And here the third identity shows that cotangent and cosecant theta are related by this identity. So cotangent is known, will help you to find cosecant theta, or vice versa. So these are the identities, and of course we can use them to solve a problem. So this problem, let's see the problem first, and we're going to decide. So from the sine, can we find cosine using Pythagorean identities? If sine is half, cosine is negative, can we determine the cosine value, or even determine all the other function values based on only the information given? Okay, so let's try to try to work on this problem. That is, okay, let's clear all drawings. And suppose I want to remind us the problem first, the sine theta is half for this theta, right? This problem, that's all we know. But we know one more piece of information, that's cosine theta is negative. Can we find the other trigonometric function values for this theta? So can we find cosine first? Let's try to solve it. The identity, we see sine, cosine are related by what? By the Pythagorean identity. Cosine square plus sine square is 1. So let's use that identity, because the sum of the squares of the cosine function, sine function value is 1. So then if sine is given, which is 1/2, the square of 1/2, right, plus the cosine square should be 1. Then we can solve it. We can find the cosine theta, because cosine square theta plus 1/4 is 1. Then at least we can find cosine square. Cosine square is 1 minus 1/4, 3/4. So cosine theta must be square root of this number. But when you take a square root, do you take a positive? You have two options. You have either positive or negative square root, right? So which one do we take? Yeah, don't forget that we're told the cosine value is negative. So we only, we know this cosine value has to be negative. That means we do not need to worry about the positive sign. We only take the negative square root. So we will take out the positive. So that is the cosine value. So now we have not only sine theta given as half, that is given. Cosine value is found to be negative square root of 3/4. But you can always simplify this quantity, rewrite it as negative, because square root of 4 is 2, right? We can keep 2 here. Square root of 3 is numerator. So that is cosine theta. So after we have sine, cosine, then you can do the quotient. Remember that we have quotient identity. Sine over cosine will give you tangent. So we can find tangent theta. because the sine is half. Divide the cosine is negative square root 3 over 2. So this is the quotient identity that allows us to get tangent theta. So, of course, when you divide a fraction, you multiply the reciprocal, right? So we can keep negative here, reciprocal of denominator. Yeah, so then that will be negative square root of 3 over 4. So we have found how many? Given sine, we have found cosine, and we have found tangent. But cotangent, can we go further? Yes, because immediately, okay, sine, cosine, tangent, right? So let's find cofunctions of each. We can simply use reciprocal property. So let's quickly to get cosecant. Cosecant theta is the reciprocal of sine, so which is 2. And secant theta is the reciprocal of cosine. Cosine is found, so reciprocal, you just flip that fraction, right? So negative, you see the cosine we found. So reciprocal of the cosine is secant. But you can rationalize it. So you get negative 2 square root of 3 over 3. And one more, that's cotangent theta, because tangent theta is this value. So cotangent is reciprocal of that. So we can put 4 in numerator over square root of 3. Reciprocal of tangent is cotangent. And then if you reduce it, you get actually rationalize the denominator. We get negative 4 square root of 3 over 3. So now we have found all the other unknown function values for this theta. So the only given piece is the sine. And also we know the cosine is negative. So using Pythagorean identity, we can find cosine, right? From sine, we can find cosine. So yeah. So after we find cosine, then use the quotient identity, we found tangent, because sine over cosine will allow us to find tangent. And then after we find sine, cosine, tangent, we can simply use reciprocal identities to find the other 3 functions. And of course, that's not the only way you do it, because you can also use quotient identities to calculate cotangent, because cosine over sine will give you cotangent. If you prefer, you can use other identities to determine the unknown function values for theta. Yeah, but you see, the more identities you know, the more options you have, and you can, it's up to you which one to use.